by the front seats.
Spelling carrier.
Students on the back rows, please occupy the front seats.
Same spelling error carry forward. Where all on like a presentation. Other carrying a random at the same spelling mistake. But it's a carrier too.
Yeah,
so
yeah,
I will spin it.
Yeah.
To all of you present here, it gives me an immense pleasure to extend a warm and gracious welcome to all the dignitaries, esteemed faculty members, and dear students to the AJCE Distinguished Lecture Series organized as part of the Silver Jubilee celebrations of Amal College of Engineering, Kayarapalli. To commence today's program, on a solemn note, may I request everyone to rise for a silent prayer.
Pennsylvania, USA. In the company, he is responsible for steering the company to support green and sustainable markets through vertical integration and diversification. He is instrumental in the organization's growth strategy as Vice President, Business Development, Chief Technology Officer, Chief Innovation Officer, and Director of India Operations prior to assuming the current role. He is a participant at various international forums in India, Europe, and North America on hydrogen and renewable energy. And he is a participating member of NFPA 2 Technical Committee responsible for hydrogen core. And before assuming this, joining this company, being the president of this company, he was also the president of managing director BTIC group companies in USA, where he was responsible for leadership for engineering operations in USA, Kochi, Coimbatore, and Pune. And he provided leadership for design, fabrication, and installation of the first indigenously built and PESO-approved hydrogen dispensers in India to support fuel cell bus programs in Delhi and Indian Railways fuel cell train project at Haryana. And he also has decades of professional career with Air Products, Allentown, USA, where he developed hydrogen fuel dispensing applications for material handling, market material handling market North America and for over-the-road vehicles in Taiwan, Korea, and India. He developed and implemented strategies of products, and he has also taken engineering management roles for industrial gases, specialty and electronic gases, cryogenics, etc. Mr. Thomas Joseph has got a master's degree in business administration from Moravian University, USA, and master's degree in mechanical engineering from Drexel University, USA, and bachelor's degree in mechanical engineering from National Institute of Technology, Calicut, India. I welcome the distinguished speaker for to this talk, and I request all my students and my faculty to carefully listen to that and keep silent completely throughout the talk, and please feel free to interact with Mr. Thomas Joseph at the end of the talk. Once again, I welcome each one of you to this talk, and I request the speaker to take. Thank you.
Thank you. Good morning. Good morning. My dear faculty, students, and I'm a fellow engineer too, right? You are going to be an engineer in a couple of months. That's what I'm told. All of you are final year engineering students here, right? I would like to be an interactive session. I don't want to stand here and speak, and also I don't want to stand here and lecture. You know, even though it says it's a lecture, I would like to see it's more as an interactive session wherever it is possible. Okay? So, because I get my energy by interacting with you. You are my energy provider. I need energy to give a very healthy speech here. Okay? So try to be more interacting as possible. If you notice the title, it is Role of Hydrogen as an Energy Carrier. It's an energy carrier, and also it's an energy carrier. So I wanted to, since it is a final year presentation here, final year students here, I wanted to highlight in between how your career could be built around the energy independence goal of India, and also around the environmental protection of the world. So as you graduate, think about what is the future, how you can contribute to the environment, how you can contribute to the energy independence goal of United States, of India, not United, sorry, of India. How many of you know what is the percentage of energy we are importing to this country? Just ballpark. Is it more than 50%? Raise your hand. No? Is it more than 30%? Can you raise your hand? I want to be interactive. I told you this. Okay, maybe it is it's ice-breaking problem. Believe me or not, when I started supporting the energy market in India, which was back in 2004, we were importing 87% of the energy needs of this country. 87%. So now you know why President Trump was able to hold Narendra Modi hostage by imposing 50% tariff on goods going from India to US. Because we need the energy from other countries. We are dependent on other countries for our day-to-day survival here. Your two-wheelers, your automobiles, your public transportation, everything is dependent upon imported energy. Today, that percentage is 82%. So we were able to improve our dependence by 5% over the last 20 years. Okay, which is really good considering the demand, energy demand of this country is going up every day. When I was growing up, I didn't have a two-wheeler or a car in my house. But today, most of the houses has at least one car, if not two cars, multiple two-wheelers. So the energy demand of this country is going up. We are all on internet and dependent upon air conditioning, all the social media and everything. So the energy demand is going up on a daily basis. So it is that 82% is not going to be a fixed number. As the demand goes up, the percentage also goes up. So we need to have means to bring it down. And the declared objective of the nation is to become energy independent by 2047. I will be touching on that a little bit deeper. But in that effort, you can all build a career. So that is also a topic of discussion here today. So briefly an outline. As you can see here, I will be touching on the challenge and challenge faced by India right now. And then I know all of you know hydrogen properties and how the challenge is overcome because of the use of hydrogen. What's the role of hydrogen in overcoming that challenge? So since we are going to be discussing about hydrogen, I will be refreshing your memories or refreshing your knowledge with respect to a couple of key properties of hydrogen and how they pose challenges to engineers, where the opportunities lies for you to find the solutions, and then how different fuels, how the hydrogen is compared to those fuels. And then hydrogen, as you know, as a fuel is used mostly in fuel cells. The reason being, if you use hydrogen as an internal combustion engine, in internal combustion engines, or versus use in fuel cells, you get better energy efficiency, almost double. So most of the hydrogen fueling application development is based on fuel cell application. So I will be touching on a little bit of fundamentals of fuel cells in case you don't have exposure to the fuel cells during your engineering career, or even if you had, just as a refresher. Then of course I will be, towards the end, I will be spending most of the time in talking about India's hydrogen mission, how India government is planning to adapt hydrogen in solving some of the problems we already mentioned, and then what is involved in a hydrogen refueling infrastructure from an engineering point of view. So most of my talk, even though I have all these topics, will be very much dear and near to some of the disciplines sitting here. Mechanical, chemical, electrical, instrumentation, civil, all those functions will be supporting this technology. Even if I didn't mention some branches, almost all the branches, engineering branches, do have some contribution towards this topic. So I will try to hit some of it. And even though Lilliput said, your principal said, I am from NIT Calicut. I passed out in 1978 with mechanical engineering degree. And I happened to be her husband's classmate. He was electrical engineering. And then we had only 3 branches at that time. And I had another civil engineering. One of my classmates is sitting here. He's originally from Kanjarapalli itself. So you're on native person here. So with that, let us get into the main talk of the day. So when I was thinking about the talk here, how to set the stage, how many of you are worried about the air quality in large cities in India? Kanjarapalli is a beautiful region, by the way. As I was coming in, I was very impressed how the college is located in a very serene environment, very environmentally friendly location. You are all breathing healthy air here. But if you take the bus, if you take the two-wheeler, if you take the cars, go into Kottayam, even Kottayam is not that bad. I'm originally from Kottayam, by the way. So even Kottayam is not that bad. But if you go into Kochi, if you have a smartphone, look at the air quality number in Kochi right now. When this statement was made by Geeta Gopinath, that was a couple of weeks ago. And she said the air quality index in Kochi is approaching 100. This morning, as soon as I got into my car, that is what I did. I just checked the air quality index in Kakinad before I started. I was surprised. It was 131. Any number above 80 is very unhealthy for us. So our goal as technocrats, as engineers, we should be supporting programs to bring that air quality index back to a healthy environment. So that's a requirement. And if you are surprised with that one, let me go to the next page. 83 cities in India falls under the top 100 most unhealthy cities of the world. Not only India, forget about India. If you take the entire world and rate the air quality indexes of different cities around the world, our 83 cities falls in the top 100. That is the crisis we have. So this is a real problem. We need to recognize this, and government is already recognizing it, but we as citizens of the country should be recognizing it too, and we should be taking care of, we should be taking steps to prevent this from creeping up and up, going to the numbers of 350, 400, 450 in Delhi and all. You all read about the problems faced by cities like Delhi, Mumbai, Calcutta. That is all because air quality index is above 400. And we don't want any of the cities in Kerala to reach there, but it is creeping up. So that's about the challenge. And then read the numbers below that. I don't want to read the slides. The particulate matter indices, 2.5 to 10. Any numbers above 2.5, my friends, is very, very unhealthy for us in the long run. If you think about why the hospital industry in Kerala is thriving, it is because our parents and our previous generations were breathing high levels of particulate matters. And we are all doing it today. So our goal should be to bring it down. I'm not scaring, and these statements are not for scaring anybody, but these are realities. So anything about 2.5, and if you know, 12 years ago, 13 years ago, Supreme Court, the High Court of Delhi came out with an order prohibiting use of diesel vehicles in public transportation in Delhi. Today, if you go to Delhi, you will not see any diesel vehicles, you will see only natural gas vehicles. It was mainly because of this. 13 years ago, Delhi was measuring 21, 22 in the PM, particulate matter index. And that is why the smog was created. The diesel generates a lot of particulate matters which results in smog. So Delhi government, Delhi court actually, stepped in and prevented use of diesel powered vehicles in the city. So this is real. Now, if you think about it, it is actually a greater health hazard due to the ability of entering into our respiratory system. So that is reality. So we need to have programs to address that. If you look into the carbon dioxide emission worldwide, India is number 3. Even though it is less than 7%, we are number 3. So that is not a good status to have. Our goal should be much lower. So what did our government do? We got into the Paris Agreement. We committed a 35% reduction in CO2 emissions year by year by 2030. So the program started about 4 years ago. By 2030, the objective is to reduce the CO2 emissions by 35%, and then net zero by 2070. So that is the goal set by our own government, and publicly it is committed in the international forums. So there are a lot of career opportunities to achieve these things. So all these commitments made by government could be achieved only through the industry, the institutions, R&D programs, all these programs stepping up. And I'm very proud to state that there is at least one institution in Kerala stepping up. NIT Calicut started formed a cell to support the renewable energy program, and I was with them for for a few times already, and I am hearing a lot of other people. IIT Chennai has a program, IIT Varanasi or something like that. They also have a program. So IIT Delhi has a program from 2008. So a lot of institutions are already starting this program. A lot of students, a lot of graduates coming out of those institutions started working in the energy sector, and also specifically for improving the environment and supporting it. And I already mentioned about the energy independence by 2047. So that is all published. Now, some of the government segments, how are we doing it? The chart on the screen speaks for itself. So right from 2019, before the pandemic, India government started supporting this renewable energy program in an aim to reduce the CO2 emissions as well as becoming energy independent by 2047. So that is an ongoing program. You can see how gradual that growth is. So as of this year, 2007 gigawatts of energy is produced from renewable energy sources, and that does not include any of the hydroelectric projects which we are familiar with in Kerala, right? Kerala and other countries, other states where hydroelectric power generation is possible. So that doesn't include. If you include the hydroelectric, it is 266. So it is getting there. Some of you are already participating in it. If your house has a solar panel, that belongs to that green bar there. If your parents, if your ancestors, if your grandparents, they installed a solar panel, you all be proud about it because you are contributing towards that goal. Now, switching gears here. How does hydrogen play in this space? Hydrogen is used as an energy storage. Again, spelling mistake there. It is used as energy carrier, and hydrogen is used in the mobility sector as fuel. So these are the three areas hydrogen plays a role. So with that, let me jump into the hydrogen. Now, before talking of hydrogen, hydrogen is already there, right? 2 hydrogen atoms on the upper left corner there, that is a hydrogen molecule. How does hydrogen look compared to the other fuels which we all familiar? So you can read the names on the board: methanol, ethanol, propane, butane, ethane. So any of the liquid fuels or gaseous fuels any of the hydrocarbon fuels we are familiar with, they are all represented. Some of the chemical engineers or chemical background folks will be interpreting this better than me. So you all know what I wanted to point out in this slide. You may be guessing already. Hydrogen is the only fuel which doesn't have a C in it. Right? So where does the carbon dioxide and carbon monoxide and all these, the unhealthy gases coming from? It is all coming from because of the C presence, right? Without the carbon, you cannot produce carbon monoxide or carbon dioxide. So hydrogen is the only fuel that doesn't have a C in it. That is the only purpose of bringing this up on the screen. So what is hydrogen? It is the most plentiful element that is available in the universe. 75% of the mass of the universe is hydrogen, right? So it is easily available. It's only a matter of capturing that available hydrogen and making it useful for us. Very similar to elephants in the jungle, right? A lot of elephants. So how to capture that and tame it and make it useful for us, and that is the goal. It's again, you can read the slide. I'm not good at reading the slides. So the nucleus consists of a single proton, and then it is surrounded by an electron, and the electron carries the proton carries the electrical charge. and the electron has a negative charge. So that is a simple explanation. And again, you being final year students in engineering, I don't want to spend too much time on things like that. Again, I will breeze through some of the properties which are important for engineers. Hydrogen it cannot exist in liquid form unless it is cooled down to very low temperatures. We engineers, we state that those are cryogenic temperatures. Anything less than 200 Kelvin is the cryogenic temperature. So very simple example, liquid ammonia, it is not a cryogen, it is actually minus 43, right? So only when it goes below minus 73, it becomes a cryogen. So you have heard about cryogenic hydrogen being used by VSSC or ISRO for the rocket propulsion and all. They actually use the liquid hydrogen. But then to get it to the liquid state, the energy consumed by the gas or by the fluid to get to the liquid stage is significantly high, and also the production facilities where the liquid hydrogen is produced, it is very capital intensive. So it is not practical to use liquid hydrogen as a fuel or energy carrier or in any of the other applications we were talking about earlier. So that is why you are reading in the newspaper, there are some programs which are initiated by the India government. Last year in 2025, there was a very big tender, one by Adani as well as another one by Reliance Corporation for producing ammonia. So what the concept is, produce green hydrogen and convert that into liquid form, liquid ammonia, NH3. Ammonia is 1 nitrogen and 3 hydrogen atoms. So once you convert it to ammonia, you need to cool it down only to minus 43. So you could easily transport that energy in a liquid form. So that was the reason why that project was, or that program was initiated by Government of India. So that is the property. Then some other properties which are challenging for engineering community. It's very odorless and colorless and tasteless. So you would know the presence of hydrogen. Guess what? You need to know. How many of you know the natural gas at home, the propane gas you are using at home for cooking? It has a smell, right? How is that smell coming? Natural gas is not, it is not odorful gas. It is odorless only. They actually add additional chemicals into the gas stream to make it smelly. So then when there is a leak, we know, wow, there's a gas leak here. But unfortunately, those kinds of additives into the gas stream are poisonous for the fuel cell. So unfortunately, the application we are talking about where the hydrogen is used, you cannot have any of the other additives because they will kill fuel cells. So in this case, engineers, we technologists, we need to come up with the means to detect hydrogen leaks. To one of the programs which is actually kicked off by an institution here in India with an industry collaboration is actually for developing leak detection systems for ammonia, for hydrogen. So that is where an engineering challenge is being addressed in India itself. And then it is an asphyxiant. Even though it is very light in gas, if it is released in an enclosed environment like this, if it accumulates, all of a sudden we will be deprived of the oxygen which we need for our survival, for our consciousness. So that is another challenge which the engineers need to solve. So if we are using hydrogen in an indoor environment, one of the commercial applications which was developed 10 years ago is use of hydrogen in industrial trucks like the forklifts in a warehouse. which is actually very common in United States and some of the developed nations, warehousing industry. Even in India, you get all the Amazon online orders. Amazon is storing those items in a warehouse, large warehouse, and inside that warehouse, the forklifts doesn't use propane gas, because then all your equipment, all your items you are buying will smell gas, right? So they use either battery or fuel cell technology. In India, they haven't used the fuel cell technology. In US, that is what they use. Then think about a warehouse having a hydrogen leak. You don't want that to happen, right? Hydrogen cannot be contained. If hydrogen is contained in presence of oxygen, all it needs is a third component of the fire triangle to catch fire and create even an explosion. So we don't want that. So that is why these properties are important for engineers. Another important property of hydrogen, it is very light gas. Its density, you can see, it's only 0.83. At the bottom, the specific gravity, right? What is the specific gravity? Again, I don't want to test you, but specific gravity is the density compared to another gas, right, which is air, right? So the specific gravity of hydrogen is only 7% or 0.0696, right? And the same thing in the liquid form, it is only 0.0708 compared to water. So it is a very light gas. So what does that mean? The next point, no, I will skip this one. I will distribute the slides, by the way. I will give you to your principal, and you will interested students can get these slides. So I will skip that. Energy content. This is where I was going with the light density gas. Even though it has light density, hydrogen energy content per kilogram of per gram of hydrogen, it's significantly high compared to the other fuels. You can see the table here. 141.86 kilojoules per gram compared to the petrol or gasoline, which is 47.5. So it is 3 times than gasoline, or it is 3 times than diesel, which you are familiar with. But you think about this before I get to the next slide. Even though the energy content per kilogram or per gram is high, hydrogen is a very light gas, right? So if you have a car with 6 liters or 6 kilogram of diesel onboard storage, that same volume is going to have only 1/7 energy content in that tank because of the light density properties which we discussed before, right? So that is the next slide. So the hydrogen energy density is very poor. So this is another engineering challenge we face as we try to support this technology. How do we mitigate that? How do we overcome that challenge? And the table below is some of the solutions that is developed in the last 20 years or so. And again, this is fundamental engineering solutions. So at the atmospheric conditions, the hydrogen energy is only 10,050 kilojoules per meter cube, which is significantly lower than, you can see, gasoline, which is petrol, which is 31 million. So 10,000 is over, way below here. 31 million is way above here, right? So how do we get there? To compete in this market, to use this, gas as a fuel, engineers need to come up with the solutions to get there. And the same challenge was there for methane, which is the natural gas which you are familiar with, CNG, right? So natural gas was 3 times, energy density than hydrogen, which is 32,000. So engineers came up with the means to compress gas to higher pressures. So you can see within that table, when you compress it to 200 bar, okay, 200 atmospheres. 1 bar is 1 atmosphere, right? So when you compress it to 200 atmospheres, you can increase the energy density by, from 10,000 to 1.8 million, right? If you increase it to 700 bar, you can go to 4.5 million. So now you are talking pretty much, even though still you are way below the 31 million, at least we are in the same ballpark. This is where that 6 to 7 number I was referring to earlier. So even at 700 bar, we are only 1/6 or 1/7 of petrol and diesel. At least we can compete there by improving the efficiency, bringing in different factors. These are the opportunities engineers have. I mean, this is a developing technology. Even though I say all these numbers, you might be reading newspapers, Toyota introducing Toyota Mirai to India, right? There are 2 Toyota Mirais, by the way. So there is one in Delhi, one in Bangalore. Those 2 Mirais need hydrogen at 700 bar. There are hundreds of Mirais running in Japan, hundreds of Mirais running in, thousands of them running in California, but in India there's only 2. And one of your ministers is driving one. And anyway, so coming back to the engineers need to come up with the technologies that can address these high pressures. Any gas, when it is compressed to higher pressure, poses technical challenges for you, opportunities for you to come up with the solutions, business opportunities for you to develop solutions. So that is the career I was referring to at the beginning. There are, if you get into the hydrogen field, it is endless opportunities right now. And there are technologies which are already developed, but still they are not mature, still in the developing stage. We all have opportunities to take it further. The other opportunity for hydrogen is using it as a liquid. And as I said, liquefaction is not cost effective, so it is very limited use today. Some other properties, hydrogen is highly flammable. So engineers need to come up with solutions to mitigate the flammable nature of hydrogen. How do we avoid the fire triangle? Right? We need 3 things to form a cause of fire. So we need the fuel, which is hydrogen. We need oxygen, which is plenty available in the atmosphere. And then, of course, you need a source of ignition. So engineers need to come up with solutions to prevent mixing of these 3 things or coexistence of these 3 things at any time. So that is another opportunity we all have. And a couple of numbers which you should be familiar for hydrogen. The low flammability limit and high flammability limit. Pure hydrogen is not flammable. You can, if it is filled with hydrogen, this hole is filled with hydrogen. If I have a scuba equipment with me for breathing, myself, I can stand in here without any problem. Even if you light it, it won't ignite. It will ignite only between 4 and 74%. So below 4%, hydrogen is not flammable. That is the low flammability limit. Above 74%, it is not flammable. That is a high flammability limit. So it is flammable only between that 2 bands there. Now, once it is in the flammable range, the auto ignition temperature for hydrogen is pretty high. It is 1085 degrees, actually 585 degrees Celsius. Once in a while I bring in the English units. The metric unit 585. So that's a good thing, actually. Now, just a refresher on gas laws. The reason I picked this slide, down the road when we are talking about hydrogen fueling applications, I will be going back to these fundamental equations here. So, being the final year students, I don't need to go through each one of the law because you already know. Because this slide was prepared way before I knew the audience is just the final year students. So I included all of them. But I know this is a smart group of engineering graduates here. So I'm not going to spend all the laws, but the one thing which I wanted to point out, the ideal gas law, PV is equals to MRT. Hydrogen doesn't behave as an ideal gas. So this equation is good, which we learned in engineering school, but at the end of the day, hydrogen is not an ideal gas. So we will have to develop, we need to have the R&D programs to develop, to calculate that compressibility factor Z, to have another multiplier when we are dealing with hydrogen. So those are the opportunities we have as engineers. Now, just an overview, the three things which we will be very interested when we are dealing with hydrogen, especially for the applications we are going to be discussing here today from an engineering point of view. Pressure. So why pressure important? As I said before, we are dealing with very high pressures. We are dealing with 500 bar, 700 bar pressures. The natural gas that is coming to your house is very, very low pressure. Its maximum is 5 bar, right? So think about, compared to that one, the gas pressure we are dealing here in hydrogen, which is a very flammable gas, we are dealing with the 500 bar and 700 bar. So we need to be very, as engineers, we need to be very sensitive about this gas pressure, and we need to know exactly how it is measured, how it is monitored, and how it is controlled, how it is managed. So some of the devices used for that, temperature. And let me, I mentioned that hydrogen is not an ideal gas. So when hydrogen is compressed, it overheats actually. So in the compressor, the equipment that is used, if you predict a temperature value based on the pressure ratio, you will find that it is not following that same curve. It is a different thing. And the other funny thing, it behaves the same way when it expands. We all think when a gas expands from a very high pressure to a low pressure, because of the Joule-Thomson effect, which you have learned, right? We expect the gas to cool down. And that's exactly how we get the air conditioning, right? The freon gas or environmentally friendly gas that is used in the refrigeration system, it is compressed and then it is expanded in an expander, and then it cools down, and that is how we get the air conditioning. Our air is taking the cooling from that expanded gas. Guess what? Hydrogen behaves just the opposite. When hydrogen expands from high pressure to a low pressure, it actually heats up. It's called a reverse Joule-Thomson effect. So if you happen to be supporting the hydrogen energy program down the road, you will be hearing this all the time. You will be hearing these questions from your regulatory agencies. Okay, explain to us how you are addressing the reverse Joule-Thomson effect when you are fueling the 500 bar or 1000 bar hydrogen from the ground storage into the vehicle. You will be asked that question, you will be asked to explain. Believe me, my team explained to PESO, which is sitting in Nagpur earlier this week, the same question. This is a day-to-day technical challenge we are all facing that I'm just mentioning. One of the means we do is by controlling the flow. So that is what the third important element in our engineering parameter that is important for us is the flow rate of hydrogen. Hydrogen being a very light gas, the flow meters are very, very, very sensitive. So if you want to get accurate flow readings, you need to have good flow meters. So that is another area, actually business area to develop, which is available. I'm going to skip these two slides. So now I believe I'm doing good with the time. How much time? 50, okay, so plenty of time. So now I'm switching gears, getting into the fuel cells. So how is hydrogen used in our applications, or how to reduce or to help the environment? As I said, when hydrogen is discussed to be used as a fuel, we are talking about use in a fuel cell. There are 3 different types of fuel cells which are commercially developed today. There's a 4th one which is being developed. These three technologies are already developed. Solid oxide fuel cells, the alkaline fuel cells, and PEM fuel cells. So I have given some highlights here. You read about them, you learn about them more. Now, most of the vehicles you are hearing about, whether it is Toyota Mirai or Tata Motors, buses, or even the train, which I have, I'm going to be touching on later, they are all working on the PEM fuel cell principle. Now, what is reaction chemistry in a PEM fuel cell? That is what is given on the screen. It is the, I think I can better explain this here. I skipped a couple of slides. So this is the fundamental working principle of a PEM fuel cell. You supply hydrogen to the anode side of the fuel cell. The hydrogen, as I said at the beginning, the properties, it has the proton and the electron. The proton will pass through the membrane and go through the other side. And what is pulling it? You supply oxygen, you supply air on the other side. So that will automatically pull the proton to the other side. While the proton is moving through the membrane, the electron is going through the resistance or the electrical circuit. Electrical engineers can explain better than me. But that is how the electricity is generated in a fuel cell. Okay, so now if I go back to this, so that this is the chemistry behind it. Chemical engineers love this. The electrical engineers may not love this one too. The architecture, what are the different components? And again, this is all in the slides. You can have it. And then fundamental, what as a general engineer, as mechanical engineer, as the applications engineer, this is all what we need to know. You take hydrogen on one side, you get water on the other side. When hydrogen is combined with oxygen, you get water, very environmental friendly, byproduct. And then in between, you get the electricity. And that electricity can be used in any electric vehicle, very similar to what you use if you have a battery-powered automobile. That's exactly what is needed here, right? I came here in an electric-powered, car. So that is exactly how it is running, except that that one doesn't have a fuel cell. So it is an electric motor that is providing the transmission, transmitting, transmission power or mobility power for the vehicle, right? And then this fuel cell can replace battery down the road. So this is nothing but fuel cell vehicles are nothing but an electric vehicle running on hydrogen. Hydrogen is a fuel. So what are some of the power, how does the powertrain integration happens in a fuel cell car? This is the pictorial representation for that. So as you said, the motor is the one that is driving the car, and the power is coming from the fuel cell, or the energy is coming from the fuel cell. So rest of it is all auxiliary equipment, accessories needed for making it as a full car. Some of the mobility applications where fuel cell is used worldwide. As I said, I already mentioned forklift. That was the first commercial deployments which happened about 10 years ago, 12 years ago. And that is globally that is adopted. It is a matured market. And there are a lot of warehouses in the United States where the forklift is used today. The passenger cars started getting into the market in 2003, 2004 time frame. Honda, Toyota, some of the Japanese companies, Hyundai, the Korean company, and China. Some of the US companies have developed back about 10, 15 years ago, but then they backed off. So passenger cars are coming. But what is being developed today and very successfully being deployed are the buses and trucks. Volvo, Tata Motors, Ashok Leyland, all of them have very healthy development programs for producing fuel cell powered buses today, and they are getting deployed worldwide. Even in India, there are few programs which I will be touching on later on. And then of course the trains I'm going to be touching later on in a slide. and ships and barges. Last week I was speaking to the marine engineers in Kochi, and I shared with some of the facts. There is actually a 300 capacity passenger ferry boat operating today in San Francisco, California, running on 100% running on hydrogen, fuel cell based. There are 3 fuel cell barges being built by Cochin shipyard. First one is already delivered to Varanasi. It is being developed by the Government of India program. It is already, the first one is delivered. 2 more will be delivered. I think Mr. Madhu is retiring this year. I met with him a couple of months ago, and at that time he said, before I retire, I want to deliver them to Varanasi. So later this year, you will be hearing news about Cochin shipyard supplying fuel cell powered boats to Varanasi. Now, for engineers who are interested in the storage of gaseous hydrogen, you will come across, when you in your practical world, when you are entering into the companies, you will hear about 4 different types of storages used for storing hydrogen. And again, I inserted this as last night just because I'm talking to a graduating class of engineers. This will be part of the presentation. I'm not going to spend time here, but look at the technology advantage. What I wanted to point out is the technology advances that happened in the last 20 years. 20 years ago, we had only type 1. All metal storage tanks, very similar to the gas tanks coming to your house, bringing the propane gas. We moved to the type 2s where it was hoop wrapped with some, from some composite material. And then type 3, we used the metallic liner and then wrapped with the composite material. And then today, the most popular storage, which is on board the fuel cell cars, is the type 4, which is polymeric liner with the composite material. If you happen to fly 787, Boeing 787 or Airbus A380, the main fuselage is built with this type 4 solution. So it is used in the airline industry and also by the hydrogen industry. Hydrogen industry is using it for storing hydrogen at 700 bar and 1000 bar. So if you are more curious about the technology, please contact me later, or you can research yourself and find it. Now, my talk cannot be completed without giving you an insight into the regulatory framework, right? Any new technologies, especially when it is entering into the common domain, right? Like any one of us should be able to go to a gas station, go to a petrol station, and ultimately fill our vehicle with the hydrogen. So without rules and regulations, it will not be safe, right? It will not be possible. So there is, over the last 20 years, worldwide, we have so many forums that were participating in developing these rules and regulations for safe handling of hydrogen, and NFPA 2 is one of the big ones. And as Professor Liligutti mentioned earlier, I was fortunate to participate in NFPA 2 from 2006 onwards, the very first, when the committee was formed, and I'm still an active member of that committee. How does that come to India? Petroleum Explosive Safety Organization sitting in Nagpur with their regional offices all over the country, they are the ones who are controlling the safety of any of the fuel dispensing, any of the fuel handling in India. And PERSO is very much connected with NFPA 2 through some of us members. And then of course the Society of Automobile Engineers, SIE, spent years and years developing protocols for safe dispensing of hydrogen. So that is how, and again, young engineers, experienced engineers in SAE, in NFPA, in different laboratories around the world, everyone put their heads together to come up with the right safety framework. Now, towards the end, I'm getting towards the end of the presentation here, or a discussion here. Before getting into the open discussion, I want to touch base on what is happening in India. A couple of years ago, early in 25 or late 24, India government came out with the National Green Hydrogen Mission. The initial investment is about $2.35 billion. And, you can see on the right side, expected outcomes by 2030. This is all related to the CO2, emission controls program and the targets, the 35 to 45% reduction in CO2 emission, committed by the government of India. So to support that program, they identified hydrogen as a key component, and then these are some of the outcomes they are expecting by 2030. I'm very proud to state, being part of the industry, being part of the technology, I'm able to monitor, and I'm reading all kinds of reports that are coming out quarter by quarter. We are on a much accelerated path, thanks to the government and thanks to the public who are conscious about the importance of bringing down the CO2 emissions for their own good, and also to achieve the energy independence by 2047. So I don't want to read the numbers here. You can see the numbers. The expected outcomes are very, very clear. Now, I inserted this slide because I'm giving this talk here in Kanjirapalli in Kerala. We should be very proud. India government declared 4 hydrogen hubs for the nation: Pune, Jodhpur, Bhubaneswar. And the 4th one you can see is Kerala. So we should be very proud that Kerala is part of one of the 4 hubs which is going to be identified for deploying hydrogen for mobility applications. How many of you traveled to Kochi airport recently? Raise your hands. Anyone went to Kochi airport recently? Okay. As you make the right turn from the highway, when you are on the airport road, if you haven't noticed it, next time when you go, please look on the left side before you go on the bridge over the railroad. Before getting to the airport, we have to cross the railroad tracks, right? On the left side, there is a BP station. As soon as you make a left, there is a BP station, which is a regular petrol bunk. We go further down, maybe a couple more miles or maybe a few more kilometers. Before that bridge, there's a BP station on the left side. It's a hydrogen station. Kerala's first hydrogen station. Be proud about it. And it is installed by BP with the help from one company in Pune as part of this 4th hydrogen hub. And the Kerala Hydrogen Valley is not going to be just in Kochi. It is going to be connecting Trivandrum to Kochi, to Calicut, to Kannur. There are multiple projects being developed by the industry, by the government, by ANERT and other folks to have multiple stations in Kerala. And last Sunday, if you were reading or monitoring the news, last Sunday, Kochi Airport actually handed over officially, or took over officially, fuel cell buses. Even though they are not on the road yet, the actual ceremony happened last Sunday. I saw the photograph and the news about it, article about it. So it is coming. It's only a matter of weeks or months before you start seeing fuel cell buses in Kerala itself. KSRTC is going to be running buses from Kochi Airport up to the metro station in Alway. That is the first route they have identified. Then we will be running from Kochi to Trivandrum. Once ANERT installs the second station in Trivandrum, there will be a bus route identified between Kochi and Trivandrum. Some noticeable programs here, especially in the south. The Chennai IIT, I mentioned, Chennai IIT has a major program for fuel cells and fuel cell vehicles. They actually signed a collaborative agreement with Hyundai, Korean company. And Korean company is actually financing the installation of infrastructure and also the research center at IIT. And then in Andhra Pradesh, there's a big ammonia production facility coming up. In Gujarat, there is one coming up. So all over India, in summary, the hydrogen programs are getting deployed through this hydrogen mission, which I have shared in the previous slide. Few other projects in India, the one on the upper right corner, that is actually supporting, we installed that, that is actually supporting 15 Tata Motors fuel cell buses in Delhi. Those buses are running within the facilities of Indian Army, Navy, as well as Air Force. So, that is an operation for the last 5 years actually. It was installed towards end of 2021. So, 4+ years now. And then there are a couple of other projects, and the most important project is this one. You will be reading about this project on a regular basis now. The blue painted train you see on the left, that is India's very first fuel cell train. It is getting deployed to run between Jind and Sonapat in Haryana, and all the trial runs, everything is completed. Now it is just awaiting Prime Minister's availability for flag off. It could happen later this month or next month. I believe Prime Minister's office is looking for most appropriate and auspicious day to make it happen. So we can all be proud. India will be the 5th nation globally after Germany, Sweden, Japan and China to run a fuel cell train. And I am very proud that my company is the one provided the hydrogen refueling infrastructure. So it's really a gratifying moment, and thank you. Thank you. Well, I didn't mention, I am actually supporting the hydrogen program in India from 2004. If you go back to this one, on the upper right corner, that old looking dispenser that was installed back in 2005 for supporting the research program at Faridabad IOCL facility. So we are integrated with the hydrogen program here in India, and it's a very proud moment when I hear about the train is getting flagged off. So anyway, so that's the train. Now for engineers, what does the piece on the right side, right? I mentioned everything on that right side is supplied by Fluitron. So for engineers, I have a pictorial, graphical representation of what is on the right side. Okay? So hydrogen is produced on site at Jind by a Spanish company through an electrolyzer, using an electrolyzer. So that is electrolyzer is important. Everything to the right of that is what our company is supporting. That hydrogen that is produced at 30 bar pressure is taken, and then it is compressed inside that container looking set of equipment that is actually made in Coimbatore. It is indigenously made, assembled in Coimbatore, manufactured in Coimbatore, and that equipment is compressing hydrogen to 200 bar as well as 500 bar. And the storage is actually coming from Gujarat. A company called AJCE is manufacturing these storages in Gujarat. And then everything to the right of the storage, we actually built before the train, we actually built at Coimbatore. So we have a facility in Coimbatore who makes all this equipment, for this industry. And then that is the two pieces which you see in the middle, towards middle right. Those are the two dispensers, and then they dispense hydrogen to the train. There are two engines, one in the front and one in the back. And we have two dispensers. The train pulls in, and two dispensers dispenses 200 kilograms of hydrogen to those two engines, and then it goes to Sonapat. So that is in brief my presentation. Hopefully I didn't run over the time, and hopefully I didn't bore you. Thank you. I think Dr. Lilikuti mentioned that there is some question and answer session. Right. So that is what I always like. I don't like making presentations. So anyway, hopefully I didn't bore you. So if any questions, Anything I could answer? Yes. You are a, that's a very good question. The distance between Jhant and Sonaput is actually marked here. It is, oh, okay. It's 89 kilometers one way. So 200 kilograms can run easily 188 kilometers, but it can run more than that. It runs about 220 kilometers. For the train. Since you asked the question about the mileage, a Toyota Mirai with the 6 kilograms on board can run 600 kilometers. Since it is a small car, right? Train needs more power. So that is why 200 kilograms, you can run only 200 plus kilometers. But the car can run 600 with the 6 kilograms. So 100 kilograms, 100 kilometers per kilogram. Any other questions? Interesting? How many of you would like to get into the energy technology sector to support the India's energy mission? Finally, students, you all should be raising your hand, right? You know about the sector before I talk to you? No? Okay. Do you know have you heard about this sector before I talk to you? Business and employment opportunities offered by this sector?
And the efficiency. What about the cost and the efficiency?
That is a repeated question that is coming up in any forum. And before answering the cost, let me address that in a different way. I mentioned multiple times, one of the commercially viable markets that was developed in the last 12 years was the industrial forklift. The second market which the industry has identified is buses and trucks, mostly buses, commuter buses. There is a reason behind it. The hydrogen production and hydrogen fueling infrastructure is pretty expensive. So when you are going to the petrol bunk and filling your petrol, you are paying 136 rupees or 160 rupees. Don't hold me to it because I haven't looked at the latest prices. Whatever you are paying not only for the petrol, you are paying for the entire infrastructure, right? For the person who is operating that petrol bunk, for the IOCL or BPCL who is producing it, even you are paying their salary too, right? The employees of IOCL salary. So that is how you should be looking at it. What is the well-to-wheels cost of the fuel? Right from the petrol, from the well where the crude oil is coming to the pump. So we cannot, today, hydrogen cannot compete in that market against the petrol prices or diesel prices. Pretty expensive. It's about 4 times costlier than petrol. But it is getting economical in locations where a single infrastructure and the production facility can support much larger consumption. So that is where the Kerala Hydrogen Valley has identified KSRTC buses running between Kochi and Trivandrum with the 2 refueling stations, one in Kochi and one in Trivandrum. So the capex can be lowered and cost could be justified. So, and then once the technology becomes more and more popular, the cost will come down. Because you need to have the user community for taking the share of the capital investment. Any other questions?
Sir,
Okay.
sir, what do you think? Will hydrogen energy completely replace the current conventional sources of energy, or will it act as a complementary source of energy?
That's another excellent question which I forgot to mention during my presentation. This is not going to be replacing any of the conventional fuels. We need all the fuels for our survival. Not only India's survival, world survival. All the energy sources need to be used. Whether it is crude oil, whether it is coal, whether it is battery, whether it is the hydrogen and fuel cell technologies, all these technologies need to coexist for our survival. The next generation, couple of generations down the road, the rate of energy consumption we are seeing today, it's going to be significant. So all these sources are needed, but they need to be managed. If the environment need to be here, like healthy environment, we need to manage them. Good question.
About the safety aspects. My doubt is about safety aspect in refilling station. What we have to be considered for safety of the person or our environment, etc.
Right. So I don't know if you noticed, during my presentation, any opportunity I was, getting, whether it is describing the property or describing the pressures, I was touching on the safety, and that is also very important. This is a concern I hear for the last 25 years. I am in this industry for 25 years now. One of the gratifying statements, or one of the most gratifying data, is that we don't have a single incident related to hydrogen safety globally from deployment of this technology. The reason being, the initial technologists, engineers who supported this technology in the early days were very, very cautious, to the extent that they were actually overcautious. So they took all kinds of safety precautions to prevent any incident, whether it is at a refueling station or a production facility or in transportation. They were very, very cautious, and through that cautious steps, and also we got significant support from governmental agencies. In the United States, all the national labs, whether it is Sandia National Lab or the Savannah River National Lab, all those national labs were funded by United States Department of Energy during a period between 2004 and 2014 to conduct all kinds of experiments and research to develop safe practices of handling hydrogen. Hydrogen is a highly flammable gas. It needs to be treated with respect, very similar to any other fuel. But how to handle that technology or that techniques were developed and validated by these national labs during that time frame, between 2006 and 2014. So about 9 year span. So thank God, all the research data is publicly available. Any of you could go to the websites of national labs and download them. Those are the basis for the regulations which are being put into place, whether it is in India, whether it is in the United States, whether it's in Europe, whether it's in Japan. All of them are there. So today, I'm very proud to say that train is going to be fueled by a technician who is just trained by us. It is not any hydrogen specialist. It's already trained. 3 technicians are already trained. They are fueling it. There's no incident anybody is anticipating.
How many fuel cells do we need to stack together to get enough voltage?
Yeah, that depends on the fuel cell. So some fuel cells produce 1 volt, right? Some 1 volt, and volt is not the only important thing. The current is also important thing, right? So the answer to that depends on the fuel cell technology, which is multiple different technologies are in there. So there's a company in Chennai who is producing 5 kilowatt fuel cell indigenously. They have, I believe, for 5 kilowatt, they have a stack of like close to 800, I believe. Again, don't hold me to it. It is their technology. We don't produce stacks. Anyone else? Any other questions? How are we doing the time? How are we doing the time? It's okay? Oh.
So how much water it produce when we use 1 kg of hydrogen?
The chemical engineers can answer that. You need 1 kg of hydrogen, how many molecules of hydrogen is used, and then 2 molecules of hydrogen plus 1 molecule of oxygen will produce the water. So offhand, I don't know. I may have it in my files or somewhere, but offhand, I don't know. What is that?
So what we do, that water we use it for some other purpose?
Yes. Well, that's a good question. That water can be, it is a potable water. It's very pure water coming out of fuel cell. You can collect it and drink it. So that is one of the ads of fuel cell manufacturers, potable water production at our outlets. Any other? Oh.
What about the efficiency of hydrogen as a fuel while comparing with the other conventional fuels?
Yeah, I think I touched on it briefly, but I didn't say the numbers. If the question was, what is the efficiency of hydrogen compared to the other traditional conventional fuels? One of the efficiency, as I said earlier, when I answered the cost, it's a well to wheels, right? When you take the crude oil from the bottom of the sea to the consumption inside our internal combustion engine, the efficiency we need to look at from well to wheels. The conventional efficiency, believe it or not, is single digits. Okay? When I make this statement, a lot of people it will be surprising to them. It's a single digit efficiency. The energy that is taken from the crude well to conversion inside our internal combustion engine. Now, if you take the same crude or same gasoline, convert that into hydrogen using steam methane reforming process, which is the most common process in any of the refineries or any of the places, which is not environmentally friendly unless the carbon is captured. If you convert to hydrogen and then use hydrogen as an internal combustion engine fuel, you can get into double digits, 14 to 15%. Now, if you take that hydrogen and use it in fuel cell, you can get to 32%. So it's a significant jump from the conventional use to the fuel cell use. It's about 4 times efficient. Any other questions? Okay, looks like the questions are over. Thanks for the attendance. It was really good. Thank you. Thank you.
Thank you all for your thoughtful questions, and a special thanks to Engineer Thomas Joseph sir for patiently addressing the queries and sharing valuable insights drawn from your vast industry experience.
Phoning in.
At this moment, I request our respected dignitaries, our principal, Dr. Veliful Jacob, our manager, Father Bobby Alexander Blackel, our director, Father Roy Pyramid, the Dean Research, Dr. Sonny C. George, onto the stage and be seated. I also request Sir Engineer Thomas Joseph Sir to come to the stage.
Good afternoon to everyone. It's a privilege to propose the vote of thanks for today's enlightening session. On behalf of Amal College of Engineering and Silver Jubilee Celebrations Committee, I would like to extend our deepest gratitude to our distinguished resource person, Engineer Thomas Joseph, for sharing his expertise with us today. Sir, your session on the role of hydrogen as an energy carrier was not just informative, but truly visionary. You seamlessly connected the air quality of India and the role of hydrogen played in solving the crisis of energy and the grandeur production that process taking place in India, which is part of India mission for energy independence. Your insights into the challenges of an engineer as hydrogen as a fuel is really appreciable. And also you elaborated the emerging trends, the initiatives taken by Government of India in various parts of India, including Kerala as Hydrogen Valley Innovation Cluster. So it's really eye-opener and encouraging for all of us. We are particularly grateful for the way you simplified such a complex subject. Thank you, sir. Sir, your time, your brilliance, and your dedication to the field of engineering and energy. We look forward to more such opportunities to learn from you. Please join me with you to appreciate Mr. Engineer Thomas Joseph and give a big thanks to him. Please.
Hello. Hello, 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 hello.
And also I would like to express our heartfelt thanks to Mrs. Thomas Joseph, Miss Anna Joseph, for her kind presence. A program of this caliber is only possible with visionary leadership. We owe a great debt of gratitude to our esteemed chairman and manager, Very Reverend Father Bobby Alex Manamplathil. Thank you, dear Father, for your steady guidance and for always steering us towards excellence. Your vision is our constant strength. Our revered director, Reverend Dr. Roy Abraham Parambil, is also with us. Thank you, dear Father, for being our mentor and leader. It is your unwavering support and active involvement in every college endeavor that provide the foundation for turning our ideas into such impactful events. A special mention to our beloved principal, Dr. Lilikuti Jacob. A special thank you, ma'am, for being the visionary behind this program. It was your initiative that brought this cutting-edge topic to our campus, and we are grateful for your constant encouragement. We also extend our thanks to our deans, heads of department and faculty members for your support and encouragement. And a special mention to the head of the Department of Mechanical Engineering, Dr. Roshan Kuribula, and the faculty members, Dr. Anisha and Mr. Matthew Joseph, and the students from Mechanical Engineering for their wonderful coordination. So our final year students from BTech as well as MTech and the Masters of Computer Applications have the audience here. You are the future innovators of India. Thank you for your active participation and curiosity. We hope this talk on hydrogen energy fuels your passion for sustainable future. Thank you once again. Thank you all.
Thank you, sir. Once again, I thank all of you present here. Thank you and have a wonderful day.